Hi, I'm Allie,
Hello, my name is Ian.
and for our project, we studied the correlation between the urban heat island effect and Los Angeles groundwater depth. For context, 30 to 60% of California's water supply comes from groundwater, and we rely on it particularly during its dry years. Some definitions related to our study you'll need to understand are firstly, an urban heat island refers to a localized and significant increase in temperature within an urban area compared to its surrounding rural or natural environments due to human presence and human activity. These areas of increased heat and rapid urbanization subsequently create subsurface urban heat islands, which are caused by impervious and low albedo surfaces like concrete and asphalt and lead to increased temperatures, which warm the ground and particularly affect aquifers, which are rocks that contain groundwater. Additionally, a thing that you'll need to understand is that a water table is the upper surface of the groundwater in an unconfined or shallow aquifer, which is what our study references. So knowing that urban heat islands lead to subsurface urban heat islands, which ultimately create temperature anomalies in shallow aquifers, we attempt to answer these two research questions. One, how have the temperature anomalies changed groundwater table height? And two, how does geography affect water table height? So here are areas of interest. This is Los Angeles County, and we mainly examined districts 3, 2, and 4. Here is the geographical location of our digital elevation model that you'll see in the next slide. It's a 3D rendering of part of Earth for context, and it helps us to understand our study area better. Here is our geographical context. As you can see, Los Angeles is filled with mountain ranges and valleys, which is important in the context of groundwater interpolation and analyzation. So as for our data mining and sourcing, we used various different shapefiles, CSV files, and Excel files sourced from many groundwater subrepositories and repositories. That was just for context, but as for our methodology, first we visualized urban heat island extent comparing daily temperature data. We layered that data onto LA County in QGIS, and we created aftermap after 2000 of water table depth, and we interpolated that data. And we examined the discrepancies finally in Sigma plot.
So a lot of our data analysis was done through these programs of QGIS, SigmaPlot, NOAA, and ArcGIS Online. And this is just a very brief overview of some screenshots that I took while doing the data analysis. So to go over our figures now, the first figure that we see displayed here is a display of temperature data over a 1-year period from 1950 and 2023. From the naked eye, this doesn't look like much of a discrepancy, but when we look at the attribute tables of these plots, we can see that there's an almost 3 degrees Celsius discrepancy between 2023 and 1950, which is a considerable amount. And then I created these plots in SigmaPlot, which show that as time goes on, temperature also goes on. And if you look at the temperature data, we can also relate it to the water table depth, and we can see that there is a positive relationship between all 4 variables. Positive correlation, I should say. And with that correlation, I mapped the water table depth onto a QGIS base map, and then interpolated it using IWD interpolation. And we can see that the areas of red are the places with the deepest water table height. And qualitatively, if we examine that and compare it to DEM model on the right, which has shape files of every single building outline in Los Angeles, we can qualitatively see that the areas of deepest water table depth is also the areas of greatest urbanization in Los Angeles. Now, to put all of these variables together, we visualize the data in SigmaPlot using a 3D mesh graph. And in the 2D plane on the XY, we can see a relationship between time and temperature, which is positive. And then I took time temperature versus water table depth, which also shows a positive trend as it goes up on the diagonal. And now so far, it's all been correlation, but to try to dispel that the discrepancy between correlation and causation, and to make sure that there is the most amount of causation, assuming possible, between water table depth and urban heat, we created another table where we examined the relationship between not temperature but precipitation. We could intuitively kind of guess that if there was more precipitation, we would assume that there would be a shallower water table height. But if we graph the relationship, we can see that's actually not the case. So we know that precipitation is an invalid variable and that it's more likely to be the cause of temperature and urban heat that affects water table depth.
As for our conclusions, we had 4 main takeaways. 1, the urban heat island effect, urbanization, and increased temperatures is not correlation but causation. 2, at any particular groundwater well study site, depth till water table increased as a function of temperature. 3, the areas of most distance till water table were in areas of the greatest urban density. And after examining various variables of precipitation, temperature, water table depth, and the relationship between urban heat islands and groundwater depth, we have determined that the relationship is not correlation, but causation.
Thank you.
Thanks for listening.